Well, hi everybody, I'm Odin. I see a lot of familiar faces. I imagine most of you know me. Don't. What I've been working on, or one of the things that I've been working on, is kind of coming up with new ways to write metaprograms and optimizing, at least in most of the material I've published so far and talked about, for compilation speed. Right? So we have the line going almost straight up and down. I mean, this is number of elements across the bottom, and compilation time is the vertical axis. And the one that's almost straight up is boost.tmp. It's what most of Boost is built in, and what most of the world builds on. This was written before variadic templates, so it's kind of unfair to benchmark them. This brown line, or the next best line if you're colorblind, is the fastest thing that's in Boost currently. This is Boost MP11. Boost HANA is somewhere in between, but it's also a little bit unfair as a benchmark because it's also doing runtime support rather than just a type-based algorithms. The next one down, the blue line, is Bridgeend, which I used to work on. And the black one down at the very bottom, that's boost.tmp. Boost.tmp is not yet in Boost. It's not even submitted to Boost, but I don't feel like renaming it. So I'm calling it boost.tmp now, so Boost with a big, big asterisk. And, you know, from talking about this and blogging about this, I basically got two reactions from people. And obviously, I like that guy, so let's put him on a pedestal. In fact, let's give him a trophy. The problem is, this guy's got a point, and not just about my drawing ability. Right? Because, I mean, you know, look at the numbers here. This is with 500 elements in, I think this was a find if operation, right? We don't, I mean, some code bases do a find if over large type lists, but most don't, right? And so sort of, can we take the same experiences we've gotten from making big algorithmically complex things fast? Basically, my former intern, Giel Douwes, benchmarked all the different operations in the compiler with a lot of compilation time because there's very high noise, so you'd have to compile something all day and then figure, well, let's see, what's the average over doing that all day compared to doing this all day? So there was a build server in our office called Bob, and Bob did nothing but build things. And you know, if you've seen this in my previous talks, there's actually one addition I'd like to make. Calling an alias with a variadic pack of template parameters is actually slightly slower than calling an alias where the number of parameters is known, because the compiler has to allocate that vector under the hood. Which means you've got some weird quantum effects of if you have some recursive algorithm that has a variadic pack of types, and then you call another one with another variadic pack of types, you basically are ping-ponging between two blocks of memory that are being allocated, and that goes quite fast. As soon as you have something that represents more of a tree, then it kind of breaks down because the allocations are slower. But again, that guy's going to tell me, nobody cares. That's not what we do. That's not how we program, right? So what's the most common metaprogramming feature, right? What do you guys use? I don't think there's been any sort of formal research on this, but I'm willing to bet it's enable if, right? And I don't make enable if any faster. And if you look at what you're actually waiting for in a normal code base, I mean, I use this to implement basically an optimizer running within template metaprogramming to optimize register interactions on microcontrollers, and that's a lot of algorithmic complexity and blah, 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 but that's not what most people do. Most people write enable if, and I'm not helping them at all, at least in all my previous work, right? So what does enable if do? Well, it's a way to induce Svine, right? This is an artist's rendition of Svine from the 1500s. So what is Svine? Well, I can use enable if and type trait to give me a value as the first parameter to enable if, and if that value is true, then I will not have Svine, and if it's false, I will have Svine, right? So this whole thing is figuring out what the return type is, even though we can't even see it because it's defaulted. We could have passed in what the return type should be, but, oh no, we did. T is our return type, or nothing, and it's Svines. Do we actually understand what Svine is, right? I mean, this was how it was explained to me back in the day, and that was sort of my understanding of what Svine is. Svine is the thing that comes out of enable if, more or less, right? That's kind of this form of explanation, right? We actually probably should understand more about what Svine is and how we use it, because it's used everywhere, and it's apparently not very well understood. I certainly learned that I did not understand it very well once sort of debates broke out about whether template metaprogramming libraries should be Svine friendly or not. And before that debate broke out, I think there was like 2 people that knew what that even meant, and one of them made it up. So one person knew what that meant, right? So if we have a very simple case of function call, in bar we're calling foo, right? And there's only one foo, so that's going to work. And types are convertible, so that's going to work, right? But the whole process of calling a function is a lot more complicated than this, and this is very, very, very abbreviated. First, what we do is name lookup. So we look in our current namespace, all the namespaces that we are a child namespace of, right? So all the way back up to the root. And then we also look in namespaces that get pulled in through argument-dependent lookup, right? So we have not only this foo, but also that foo, right? And then the compiler will try and figure out what the best match of those two are. And then argument-dependent lookup means there's an A somewhere else, an A namespace. We don't look in there. Even if there was a foo in there, we wouldn't find it, right? Unless somebody takes some type out of that namespace and passes it to our function, right? In this case, it might be very surprising to the author of B and C foo that the namespace A is also in there, since they don't have anything from A in their function parameters. Let's say A is boost, or A is upsell, or A is standard library, or whatever. Somebody down the road puts a foo in A, and suddenly the world breaks, right? Because that foo is a better match, and because we're relying on the implicit conversion of S1 to bool, that gets dragged in, and yeah, stuff breaks, right? So this is actually not metaprogramming. For once, there's something that breaks in weird ways that's not metaprogramming. Then we have a bunch of other rules that are, for member functions, and that just gets, yeah. Then we have template argument deduction, right? So if there is a function template that's found via name lookup, then we will try and deduce what T must be. In that last call case, it would be S1, right? And then we will test, is S1 constructible from an int and a bool? Well, no, we didn't have any constructors on there. So this is going to Svine. That means it's being taken out of the candidate set for overload resolution. The important thing to understand here is the compiler can't decide where it does template argument deduction. It has to, because whether it did or not is observable based on the point of instantiations of all of the templates that go in there, right? So if I have first parameter will match one function and one function only, and then there's a bunch of other templates that cannot match because their first parameter is not a template and is not convertible, the optimizer can't just say, hey, I know that won't win overload resolution. It's not a match. Well, it's part of the pool of candidate functions. And so the compiler has to try and deduce the types and see if they swine, right? So we actually spend a lot of time waiting for swine, right? I mean, if there is some function in the overload set that is a candidate and it takes an optional, I have to test if whatever I put in there is convertible to an optional. And that's like 16 constructors that all need a swine, right? So most of the time, we're waiting for the compiler. If nobody's doing any ninja stuff, then we're basically waiting for things to die, right? Which puts a very sort of depressing connotation into this talk, right? We're waiting for all the swine candidates to get removed from the overload set. If you look at the current ranges library, there's a lot of stuff that's swining in there. That's why it takes so damn long to compile, right? A while back, I was very very excited to make ranges faster because I'd figured out how to make metaprogramming faster, and then I started looking at it and like, I can't really help this problem because it's just too much swine. So this talk is about how I finally can maybe help this problem, right? But let's look at some more swine cases, because after having arrived at all of that knowledge, I still didn't understand swine, because swine is also a return path, right? Common type will give you either a common type or it will swine, right? So it's kind of like an exception, if you will, right? So either you get the result or a swine death, swine error, not an error. You get swine, I don't know, I even know how to talk about this, right? I mean, and in this case, if there is no common type, we probably want to remove foo from the overload set, right? Because this foo just doesn't work, right? And if we have some meta function that we're passing common type to as a sort of template parameter, and then the parameters, and then somewhere in the guts of this meta function, we call common type. Do we expect the swine to bubble up to the top level and remove this from the overload set, or do we expect a hard error? In this case, we probably expect swine. And this is what's known as swine friendliness, right? If there is an error anywhere in a template metaprogramming library, as in I passed in types and the library is expecting them to have some property and they don't, I want that to swine and that swine to bubble all the way up to the top to whatever context I'm in and have things swine, right? And this is sort of a debate that broke out during the review of the boost.tmp library. Whether we want to be swine friendly or not. And boost.mpl is mostly swine friendly. I'm convinced completely by accident because it's not in the documentation, and it's only most of it. MP11 is also mostly swine friendly. I think there is a bit about that in the documentation, but at least during the review process, at that point in time, it wasn't completely swine friendly. There were some contexts where it wouldn't propagate swine. Metal, the last one in that column, by Bruno Dutra, is, as far as I reviewed it, completely swine friendly. It was a nice thought experiment of whether we could actually do this. And he was a very integral part of the whole debate. Eric Niebler's Meta is also mostly swine friendly. And then there's the libraries that I had anything to do with, Quasar MPL, Bridgend, also boost.tmp in its very first version, and boost.tana. They basically ignore the problem, so sometimes they're swine friendly, and most of the time you get a hard error, which actually might be what you want, because it might be a case of, hey, this is not a good candidate, but it also might be a programming error. It might be total luck, right? So if foo gets removed from its overload set and it's total luck, it's, you know, somebody passed me garbage long, long time ago, and therefore I am hitting this error now, there's probably not going to be another foo that in that overload set that works, right? So I'd get a hard error there that there's no foo in this overload set, and then you, oh, well, okay, that's because something really deep here is FINA'd. Maybe you have a chance to find your way back to the error. Problem is, in newer code, we like to sort of pass the return type along, deduced. We also pass along SVINE, right? This is a SVINE context. So if bar doesn't find the right overload for us, then there will be no foo. And whoever's calling foo might be doing the same thing. So what was actually a programming error or a input error or whatever, what have you, may actually propagate a long distance from one overload set to another overload set to another overload set. And there, somewhere along the way, there might actually be another candidate that works. And that might be very unexpected. It's also slow. Oops, I had that highlighted. Even newer code, we'd probably just write this. Is this going to propagate SVINE? No. Why? I don't know. We could put a deduce no except on this. That won't propagate SVINE. We could, if this was a member function, we could put a, you know, one of those C++ 20 Boolean explicit thingies. I believe that will be a SVINE context. So where we propagate SVINE and where we don't is not super clear. And most people don't understand this, and including myself until like a couple weeks ago when I researched all the cases. And it could just subtly break. Like it'll probably just be an error that's just really hard to find, right? But it could subtly change the overload that's called, and you're never going to figure out why. And you're not going to expect it, right? Because it got drug in from the function that you called, the function it called, the function it called. Something changed there. Maybe somebody added an overload to some other overload set that got drug in by ADL, which caused something to be ambiguous, caused the whole chain to SVINE, and now you have problems, right? The problem is, our example case was also like a super easy example of what SVINE looks like. Most SVINE looks like this. This is from Abseil. And I chose Abseil because it was actually the cleanest implementation of optional that I could find, right? That was actually standards compliant, right? So this is one constructor, one of the many constructors in an optional, and they're figuring out whether they need a SVINE or not. So I'd imagine there's some library implementers in the room who can tell me what this is for. I mean, it is a C++ 17 feature, so it's a little unfair. There is a standard conjunction. This is the Abseil conjunction, which mimics the implementation of the standard conjunction. Standard conjunction is basically a lazy and, right? Because in normal programming, if we have this and that and that and that, it will short circuit, which we learned at the Diego's quiz, right? So you can get around undefined behavior, you can get around all sorts of stuff because of short circuiting. Metaprogramming and doesn't quite do that, right? If we were to write like that like this, rather than this, then it wouldn't be lazy. It wouldn't be short circuiting. We would instantiate all of the types and then figure out if the value is true or not, right? The problem is that we are a constructor taking one template parameter. That means we could be the copy constructor. And the is convertible and is constructible are implemented in terms of swinaying on an attempt to construct the thing. Right? So we have to be short-circuiting in order to not make infinite recursion happen. Right? Conjunction was also billed as, hey, it'll compile faster because we can be lazy. That's actually mostly a lie. But we can't write code like this because it'll short-circuit, right? In terms of the compilation speed advantage of conjunction, the question is, like, what's the common case? It probably is faster if the first thing in the conjunction is false, and then you can short circuit, right? But if we have sort of this use case, well, the top foo, that's a candidate, right? It's not going to win, it's not going to match, but it's a candidate, so we have to figure out whether 2, an int, is convertible to an optional of s. And not knowing what s is, maybe, maybe not, right? It's definitely not going to win overload resolution, but we do that, right? So in resolving overload resolution here, all of the constructors of optional have to swinay. And if we're talking about all of the constructors having to swinay before we know, oh, this is not convertible, right? Then we are probably going through every combination of everything that was in that conjunction, right? So being lazy isn't buying us anything because we're doing everything anyway. If we had this use case, well, a 1, let's just assume it's not convertible to an s. In that case, we don't have to test the optional conversion thing because that's already not a candidate, right? So how conjunction works is you pass it unevaluated metafunctions, and it will evaluate them, as in call the colon value or colon type. In this case, colon value. It will instantiate them one after another as long as the result is true, right? And so testing for is same of in place t, or input decayed, as in we take away reference and CV qualification and blah blah. Testing if it's an in place tag. That's not the common case, but we're doing that first for some reason. That we are the copy constructor, that's probably also not the common case. I mean, the vast majority of cases where I test if A is convertible to B, they're not the same thing, right? So I'm going to get to here in almost every case anyway, right? So the laziness is not buying me anything. It's just stopping the compiler from from infinite recursion in case this is the copy constructor, right? Or a candidate for copy constructor. This decay thing here is actually, ironically, one of the most expensive things we're doing in this entire operation, and we're doing them eagerly, right? We're not doing them lazily. Because decay itself is implemented in terms of a bunch of swinay, right? I mean, I don't really have time to go through all this, but I think there's like 3 or 4 cases of swinay, depending on what type you put in, to figure out how it decays, right? And all of this internally is also eager, right? So no matter which path you take through here, all of this is getting instantiated. And when a function, when a class template gets instantiated, the compiler has to remember it for the rest of your compilation, right? I mean, every single possible type that I throw in here, I'm instantiating maybe 20 different things and a couple of function templates, and those are going into hash tables in the compiler. And although we can get towards sort of amortized constant lookup time in a hash table. In theory, we can't do it in practice because the bigger the hash table is, the larger your probabilities for cache misses are, and the larger your probability of needing to rehash things, or there is no perfect hash, so you have hash collisions and blah 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 blah, right? So adding a bunch of types to the compiler doesn't only just use a bunch of RAM and take time to add them, it also makes the rest of your compilation process also slower. Right? So we don't want to instantiate as many types. The problem is that's really hard to do. Because if we want to be lazy here, how would we even go about doing that? Right? We can't say, hey is same. On your first template parameter, don't call : type on that. But on your second parameter, call : type on that when somebody calls your : type. Right? It's just not supported by the paradigm to have some things be eager and some things be lazy. Right? And that's probably actually the reason why they use decay in the first place, because this is more complicated than it really needs to be, because they don't actually need a decay. All they need to do is remove the const volatile qualifiers and the reference, but not, have an array decay to pointer and all the other crap that they do, like a function pointer to, all of that stuff, right? And that's where a lot of the Svine tests are. So I actually had this in my slides at C++ Now, and one guy noticed, this is actually an error. You can't quite be this lazy. You'd actually have to put the : type here. Almost works. And it's because of these sorts of, if this was a standard conditional, this would be the way to be lazy, right? So it's kind of a bunch of jumbled up ways of being lazy and eager, and we have the _t versions of all of the traits classes to be eager, so we don't have to have, say, type name and : type and all that. Problem is, how do we be lazy with those? Right? So we have two sets of all of the traits so that we can pick if we want to be eager or lazy. And the other ironic thing is, you might think, okay, so at least we're testing if we're convertible, and we don't have to test if we're constructible. At least we're short-circuiting on that, and we're saving ourselves that thing, right? If we're not a candidate for the copy constructor. Then let's look at the next constructor. Oh, I negated that, so I'm definitely instantiating the is constructible as well. Right? So I mean, sort of first takeaway here is that conjunction, because of the best match way that we resolve overload sets of constructors and other things, conjunction does help us on compliance and not building infinite recursion. It probably doesn't save us any compilation complexity, right? Because there's probably another permutation that you're testing somewhere else, which is just instantiating everything anyway, right? So compared to this, it's not actually faster. It's just a compliance thing, right? Which is too bad, because there is some potential to be faster here. If we think of sort of a traits class, right? They're all sort of this pattern, right? You have is a this or that, or is constructible or whatever, and you return from either true or false, depending on whether, or you derive from either true type or false type, depending on whether the trait is true or false, right? Then we have a alias version, which calls the : type for us, and therefore is more ergonomic, but also not lazy. The problem is, for every t that anyone ever passes in, we're instantiating this class template and filling up all the hash tables. And I mean, it's an allocation inside the compiler, and allocations are slow, and this is what we're waiting for most of the time while we're compiling. Whereas, most of the, most of the traits are actually intrinsics. They're just magic functions, right? And this magic function, well, how is same implemented? Well, probably super easy. Give me 2 pointers to types, and I say, hey, is that the same pointer? Yes, no, right? So why couldn't we just have the _t version just return us a true type or false type, depending on what that thing is? Then I've instantiated 2 types rather than n types for n different kinds of t. Because it's technically observable. And the standardization standardize it the other way around, right? But it would make things a whole lot faster, right? Blue line, top line is the is stem from the standard library, and the orange line at the bottom is same alias, right? You might say, oh, wait, but these are unique instantiations, right? So this is 500,000 different types that I created. What about memoization, right? If I have already created the type, then I just need to look it up, right? Let's say, okay, about 10 of each type are the same type, right? So 10,000 less types, but each one 10 times. Well, this green line, that was the standard library version that's instantiating a type 1 out of 10 times and looking it up 9 out of 10 times here. And the other one, well, didn't change in complexity, besides the noise, because, yeah, it's not memoized. And if we do 100, well, I don't know why this got a little lower. That's probably noise, maybe some cache effects, I don't know. This one didn't really get lower, right? I mean, no matter how many types you do, calling is same intrinsic is faster than looking up the 2 types. Sorry, looking up the is same instantiation of that trait, right? And this is probably actually cheating, because all I'm doing is looking up the instantiation of that trait. So the cache is hot, right? In a real program, the cache would probably be cold, but comparing 2 pointers doesn't rely on cache looking up memoized types does. So there is potential to actually be faster here. Maybe, what, 2x or something? Not quite. But 2x a lot of times, right? Because all of those types, well, I mean, I guess it depends what the common case is. For lookups, 2x, it's more like 5 or 6x for making new ones. And the problem with InSame is there's a lot of combinations of 2 types, right? I mean, the amount of IsSame traits that you have instantiated in any given translation unit is going to be huge. But actually, conjunction itself, the way it's standardized, also creates a bunch of types, right? Not only does it force an interface where we actually have to use a class template, and have to instantiate a class template for every one of the options, also its implementation itself instantiates at least 1 new class template per element that you have in here, because it's recursively going through them, right? So to benchmark this, let's simplify the problem to this, right? I mean, I have 4 different 4 different traits tests, and I'm doing a conjunction on them. And in this benchmark, it will short circuit sort of at the first one, right? Because obviously they can't all be true. So this is the short circuiting case. And yet, the green line, the conjunction of the 4 of them, is a lot more than 4 times slower than 1 instantiation of IsSame. The actual complexity is 1 instantiation and then short circuit. But the actual implementation of conjunction is taking up a bunch of our time, right? The red line here is the fastest conjunction that I could write that I think is still standards conforming. It's implemented differently. The orange line that popped up down at the bottom, for reference, that's how long it takes to call the intrinsic. That's how long it really should take, right? So I can't quite get down to that red line because there's going to be some overhead of the system. But if I'm allowed to change the paradigm, and we're getting to sort of boost.tmp implementation here, I can at least get to the purple line here, right? Which is certainly faster than anything else. It's also a more powerful paradigm. We'll see in a minute, right? First, in order to understand how boost.tmp is implemented and why I can do things that the standard library can't, I have to understand what boost.tmp actually stands for. It's tacit metaprogramming, right? People are familiar with the tacit programming paradigm? You all are, just not by its name, right? This, for example, is a tacit program. I don't say how the arguments get from sort to unique on the shell. I pipe them in, right? I don't name the names of arguments. I just say the output of that goes into the input of that. And there are several other manifestations of this. Haskell point free is probably a lot of people's favorite version of this. Some other people call it Haskell pointless. We're getting a manifestation of this in the standard library. It was recently voted in, I believe. C++ 20. Ranges. Ranges are a tacit paradigm, right? I have a thing, I pipe it into the next thing, I pipe that into the next thing. And I can write my program without actually naming the parameters that go from one to another, right? Tacit is actually a synonym for quiet, right? It's quiet because I don't name a bunch of this stuff. So how does boost.tmp work? Like, what does its syntax work like? Well, if I were the king of everything, it'd be something like this, right? I have a pack of arguments, and I can pipe that pack of arguments into whatever I want, including a function, right? This would essentially be standard apply, if you will, right? I have a pack of args, and I call bar with those args, right? This will obviously give me an error if the size of the pack of args is not 2, and they're not both ints, or at least convertible to them. But it also has other problems, right? Okay, so this is how I'd call it. The problem is I can't just pass around an unexpanded pack in C++. I can do something similar in Python. Their packs are kind of more first-class citizens. In C++, they're not. They need to be expanded. So if I want to pass it around, even conceptually, I actually need to make a fake pack, which is some type that wraps a pack. Then I can pipe that pack into anything I want, right? This I could implement, but it's actually dangerous because you cannot capture an overload set by reference. You can only capture a function by reference. And as long as there's just one, this will work. If there are ever two, it will clash. This is generally a problem in C++. I can get painfully close because I know on the left-hand side exactly what arguments I will be calling bar with. I just don't know its return type, so I still can't deduce it. Right? But with a macro, I can capture an overload set. Under the covers, I'm making a generic lambda, and in the lambda, I'm calling bar, and at that point, I know what I'm calling it with, and so overload resolution works, and everyone's happy except for people that don't like the preprocessor. So I'm not quite that happy with that, but it's the best I can do, right? So this is a pretty powerful paradigm, because just like with ranges, I can say, hey, I can add something to the middle of that. I can take a pack, I can pipe it through a filter, and then I can pipe that into my call to bar, right? So I call this with a bunch of blah blah and a default constructed baz, but the only thing that's going to get through that filter is the 1 and the 2, right? So going through the first pipe is all of those parameters. Going through the second pipe is just a 1 and a 2, and so that's what we're calling bar with, right? Because filter takes most of them out. Just, the same way as a range, the difference between this and ranges is I can have different types because it's a pack of, a pack of arguments rather than a range. But conceptually, it's actually very similar. To sort of exercise our visualization ability of this paradigm, what goes through the first pipe? Everything. What goes through the second pipe? Well, okay, I'm indexing. My indexes start at 0, so that would be the 1. At index 3, 0 base 3 would be this one, right? So going through this pipe, we have this parameter. And then we have a pushback. So what's going through this pipe? It would actually be a 1 and a 6. So that's what we're actually calling bar width. Right? So I don't need like a bind front or a bind back or placeholders or any of that other stuff that I have in other metaprogramming libraries, because I can just manipulate the pack the same way I'd manipulate any other range. Right? I still can't quite get the syntax. I can get painfully close, but I also want this all to be lazy evaluated so it compiles very quickly. Right? And in order to get that to happen, the problem with lazy evaluation of expression templates is, when do you stop being lazy? Right? Used to be, before we had auto, you could say, oh, when the user wants to be converted to their type, well, then my conversion operator to that type, that will do all the actual eager evaluation. Now with auto, you can't do that trick anymore. So people in the standards committee are talking about operator overloading operator auto. So if somebody wants a conversion to an auto or auto deduction, then you say, hey, auto on this means that. I'm sure it will be quite contentious. I have no idea if it's going anywhere. Would help us here, but I want this to work in C++11, so definitely can't use any 20 or 23 features. So I'm going to define syntax here. Pipe means lazy, and monad bind means eager. And I'm going to duck here in case there's any Haskell programmers in the room. Nobody threw anything. Good crowd. It actually is probably annoyingly close to a monad bind if you think about it right. We could also put that operator everywhere or other places, and it would just eagerly evaluate other things, but being lazy is good, right? So this is the sort of equivalent of boost HANA, where we can actually operate on tuples, runtime and compile time types, right? But it's a slightly different paradigm than HANA, which allows us to do a lot of optimization. Because from up at the top there, in my little monad bindy thing, I can look down the entire tree and see all the things that the user is going to be doing before I actually do them. In HANA, I'm returning a tuple at every point in the chain, and I can't do sort of large-scale optimizations. In this case, I can. There's actually a bunch of other stuff under the hood. This is actually very young. This syntax might change, and I can't give like super good benchmarks because I'm not quite sure if the way I've implemented it now is the way I want it to be long-term. But it looks like, somewhere close to an order of magnitude more performant than HANA on the same tasks, right? But boost.tmp wants to be, 2 orders of magnitude faster than HANA on type manipulation, right? So we can't actually use this exact syntax. This is a syntax for type and value semantics. If we just care about types, we can do the same thing without all the function calls, right? So I have my operation. It's at with that parameter of uint3. I call my operation on a pack, right? So this operation up here The at underscore with its parameter uint3 is actually more like a lambda or a functor, if you will, or a closure as they're called in other languages. So I'm just making up the term template metaclosure. Template metaclosure is a type that takes fixed parameters and also has some secret function call operator, which is invoked using the call macro, call underscore. And so we have one fixed parameter of uint3 and a bunch of dynamic parameters of int, bool, char, float, blah, blah, which are passed to its function call operator. Because it has two sets of input parameters, one fixed and one variable, I can compose them through the fixed parameters, right? So this is just an at, and if I want to say I want to pipe the result of this into something else, every one of these template metaclosures has a defaulted last, in air quotes, template parameter, which is the thing it's getting piped into, right? So I have an at, which is piped into pushback, because pushback is its last parameter. Pushback will push along to the back and pipe that into its last parameter, which is same, right? You just can't see the pipes anymore, right? Because we can't do pipes in template aliases, right? But it's the same paradigm, right? So going through the first imaginary pipe is going to be a long, because that's the index 3 starting at 0, right? And then we're going to push to the back of that pack, another long, and then that pack of 2 is going to get piped into is same, right? So this will return true. Right? This means that we can actually compose things in a different paradigm where we can be lazy by default, right? It was very, very hard to be lazy in the implementation of the constructor of optional. In this paradigm, we are lazy by default. If there is a short-circuiting possibility, we will short-circuit and you don't have to do anything, right? This is underscore is a version of is same where the first parameter is fixed and the second parameter is the thing that came in through the dynamic function call, right? So we're going to test if it's int, and if that's true, we're going to test if it's bool, which is already stupid because one of these is going to short circuit, right? But you could put other things in here, and you basically have a short circuiting decision tree. You might notice I left out all the else's, right? The default else is a nothing type, which is a concept from functional programming. If you have, or it's sometimes called nil or whatever, none. So if one of these ifs results in a nothing, then down the chain, nothing more is going to be called until I hit a or else, right? And the or else will only be invoked in the nothing case. And so we're going to either be true or else we're going to be false, right? But this is a more powerful paradigm because I could leave out the or else and I could call it maybe rather than call all the way at the top level. And the semantics of maybe is if it encounters a nothing, it will sphene. Right? So here I could be working out which tag this is for tag dispatch in a decision tree, which is actually lazy and not going to instantiate all the permutations because it's not best match, it's decision tree. And then if I can't figure out which tag it is, I'm just going to sphene. Okay. And if I have a nothing type to represent nothing, I can also create my own sphene context and catch the sphene and turn it into a nothing, right? So if you want to test if a type has a member function foo, you make an alias to decal type of that type : foo and say try, and either you will get the return type of that foo or you will get a nothing. SVNA will not propagate, right? The nothing will propagate. And if you said maybe at top level, then it will turn back into a SVNA error. If you use it in a context that doesn't support propagation of nothing, then it will be a hard error. So in other words, you can choose where you want SVNA and where you want a hard error. So if we look back sort of at this example, the general problem here is that we have something like 16 constructors, and they all need to SVNA. That's going to take a lot longer than one constructor that may or may not SVNA and will dispatch to a delegating constructor based on tag dispatch. Right? That will compile a lot faster. So the sort of best match and then we SVNA out the ones that don't match paradigm is, I think, one of the reasons why compilation speed is so slow. It's the only way to go if you have an extensible set, right? If you have a set of overloads and the user can write their own overloads to extend that set. Most sets are not extensible or only accidentally extensible, right? I mean, if you write your own sort that needs to take part in resolution of standard sort, then you better not put it in the standard namespace. You're not allowed to do that. And if you do a using of both namespaces, then, and then call it unqualified, then it may work today. It probably won't work long term because somebody else is going to write their own sort and it's going to clash. And you probably can't control that, right? So most sets, I mean, constructors are certainly a bounded set. You can't write constructors for other people's classes. And most other overload sets are relatively fixed. And whenever you have that, you can write one template that swallows everything and will SVNA if it's not good, and then will tag dispatch to the right one. And the advantage to that is you can still do best match if you want. You can also do first match. Right? I mean, we put a lot of effort into making one function template a better match than another function template arbitrarily because we don't actually want best match. We have, okay, this algorithm's the fastest, then that one, then that one, then that one. And so if this one matches, we want to go with that one, even if the types don't have to convert as much for that one because it's slower, right? So we actually ended up talking a lot about other problems. I imagine at least somebody in the room came here to see a bunch of crazy shit. Right? We can also implement toString, completely in templates, completely in this domain-specific language. Right? This will take a number, as in a integral constant, and turn it into a pack of integral constants, which are the chars that this string turns into. If you have a toString, you can implement a really wicked fizzbaz, right? Or fizzbuzz. This is fizzbuzz of 0 up to 1,000. And it renders everything toString, so you'll get a nice pack of chars coming out of the other end of this, which are 1, as in, letters 1, comma, 2, comma, fizz, comma, 3, comma, right? All the way up to 1,000. And it compiles pretty fast. And this is sort of a visual approximation of that happening. Yeah. If you want to contact me, I'm Odin the Nerd at all of these places. And we can open up for questions.
Hi. Can you do multiple eager computations, like with the greater equals operator in a row? It's like a trick question.
Maybe. I don't know Haskell well enough to... I'm actually not a functional programming buff. I've discovered a lot of this accidentally, and people have come to me and said, hey, that's a thing in Haskell, and this is what it's called. And I'm like, damn it, I need to rename that function.
The issue is that And if you overload the greater equals in C++, unlike Haskell, it's right associative. So you have to be careful with that, or it limits the utility.
Yes, it is right associative. It also binds later than the bitwise or the pipe. And so basically you compose the entire pipe and you have your pack, and then that operator gets called. It actually still works if you do that operator later, because you can only call that with a pack, and so it'll propagate the right direction anyway. It's constrained in that way, right? So it will try to convert the other thing to a pack and then evaluate it, and yeah. So you could only do that if you wanted to be eager in every step and get rid of the pipe if you wanted to, but it would be slower because it's not lazy. Any other questions? I intimidated everybody. Oops. Or you're all still just dazzled by my awesome unicorn. Let's watch that again. Oops. There we go. Okay, thanks everyone.